Hello viewers, welcome to the video number 99 of the channel MALACHEMPHILIC, and video number 99 is the 40th episode of Chemical Thermodynamics. Topic of this episode is entropy changes in irreversible processes. In my last video, I have discussed the entropy changes in different reversible processes where you have observed that total entropy change, that is entropy change of the system and surrounding in reversible process is 0. Now let's see what happens in irreversible process. So let's start. So our topic is entropy change in irreversible process. Okay. So entropy change in irreversible process. You know that entropy is a state function. So for the system, entropy change in the irreversible process will not depend on the path. That means, what I want to tell, entropy change of the system in reversible process will be same as that of irreversible process. So, for irreversible process also, we can predict the entropy change in the reversible process, or reversible path of transformation can be located for the system. Okay. So for the system, we can write like reversible entropy change equation for the system. Delta S system, which you know that NCV ln T2 by T1 plus NR ln V2 by V1. Okay. Now, before going to the actual topic, one thing I want to clarify, want to tell you that, see, we know that from first law of thermodynamics, from first law of thermodynamics, what do we know that Q reversible is equal to delta E plus W reversible. Okay. W sign is for expansion negative, for contraction positive, whatever it is. Just we are not considering the sign here. That is, heat absorbed is equal to change in internal energy and the pressure volume 1. Okay. Similarly, Q irreversible is equal to delta E plus W irreversible. Okay. Internal energy is a state function. So delta E here and here same. So now equating these two equations, or we can write delta E is equal to Q reversible minus W reversible, and again from this equation delta E is equal to Q irreversible minus W irreversible. So equating these two equations, Q reversible minus W reversible is equal to Q irreversible minus W irreversible, and we know that W reversible, work done in reversible process, is maximum greater than W irreversible, since therefore this is greater than this one and both these are equal. So therefore Q reversible greater than Q irreversible. Remember this point, that heat absorbed in the reversible process is more than that of the heat exchange in the irreversible process. Now we'll come to the actual topic. Our topic is entropy change in in isothermal irreversible expansion of ideal gas. Okay. Here we are considering two things. One is number one, first one is that is free expansion. Free expansion. Free expansion means expansion in vacuum. So it is expansion in vacuum. Okay. Or here you can write P external is equal to 0. Okay. So like this. So expansion taking place by moving the piston. Here is the gas. It is expanding against vacuum. That means there is no external. P external is 0. Gas is moving by gas is expanding by moving the piston. Okay. So this is the first case. So now delta S system, already I have written the equation, that is NCV. As I told you, we can follow the reversible path of transformation because entropy change is state function. NCV ln T2 by T1 plus NR ln V2 by V1. Now, as it is isothermal irreversible. So, as it is isothermal, delta T isothermal, therefore, delta T is equal to 0. No change in temperature. T constant. Okay. Then, delta S system, that will be is equal to NR, because this part will get cancelled, NR ln V2 by V1. Right. Now coming to the delta S surroundings. Delta S surrounding, how can I write? This system has absorbed heat from the surrounding. That means surrounding has released the heat. So, this I can write it as minus Q irreversible. Surrounding has released this much of heat which is absorbed by the system, that's why negative. So, this is in terms of system divided by T. Okay. And this Q irreversible, just now I have shown it to you that this Q irreversible, that is equal to, I can write it as delta E plus P delta V, that is P external delta V. In this case, as it is isothermal, temperature constant, so delta E is equal to 0. So Q irreversible, that is equal to 0, plus external pressure is 0. So this is also 0. So Q irreversible is 0. Okay. So delta S surroundings, which is equal to minus Q irreversible of system divided by temperature, and Q irreversible is 0. So 0 by T is equal to 0. So total entropy change, which is the entropy change of the universe, that is delta S system plus delta S surroundings, that is equal to, delta S system is how much? Already we have derived, NR ln V2 by V1 plus delta S surrounding, which is 0, Now V2, it is expansion, V2 is greater than V1, so this part is positive, so it is greater than 0. So in case of this free expansion, total entropy change of the system and surrounding is positive, that is greater than 0. Now case 2, second case. Second case is expansion, that means isothermal irreversible expansion of ideal gas. Expansion at constant external pressure, say P external. Okay, in this case what happened? Okay, here also delta S system, that will be is equal to same, that is NR ln V2 by V1, and delta S surroundings, that is equal to minus Q irreversible of system divided by T. Okay. And minus Q irreversible, already you know, that is Q irreversible, that is equal to delta E plus P external into delta V. And as it is isothermal, delta is 0, temperature constant means no change in internal energy, plus P external delta V. So delta S surroundings, that will be is equal to minus, in case of minus Q irreversible I am writing, minus P external delta V by T. Okay. Now what is the total entropy change? Total entropy change, that is system plus surroundings, delta S system plus delta S surroundings, that is equal to what? Delta S system is same, this is our delta S total. Delta S system is same, that is NR ln V2 by V1, and delta S surrounding is minus P external delta V by T. Okay. Now this part, minus P external delta V, this is nothing but the Q irreversible. Okay. Already I shown you earlier also, that is Q irreversible is equal to your P external delta V, and Q irreversible is less than Q reversible. So this part is less than Q reversible, and for system we have considered the reversible part. So this one is less than this one. So therefore this part is greater than 0. Okay. So entropy change in the irreversible isothermal expansion, where expansion takes place under constant external pressure, that is greater than 0. So it is spontaneous. Okay. Now the next one is entropy change in irreversible adiabatic expansion of ideal gas, right? Achha. In case of system, I can write the same thing. Okay, delta S system, because I can consider the reversible path of transformation, because entropy change is a state function. So NCV ln T2 by T1 plus NR ln V2 by V1. Okay. Now adiabatic means system is insulated. No heat can enter to the system from the surrounding, or no heat can release from the system to surrounding. So no heat exchange. So entropy change of the surroundings, okay, which we can write minus Q irreversible process, no, irreversible by T in terms of system. This Q irreversible surrounding has not released any heat. So this is 0 by T is equal to 0. So total entropy change of the system and surrounding, that is delta S system plus delta S surrounding, that is equal to what? NCV ln T2 by T1 plus NR ln V2 by V1. This is for system plus surrounding. So it is greater than 0. So entropy change in irreversible adiabatic expansion, total entropy change, that is system plus surrounding, is 0. Now if we sum up all this entropy change in all this process, what we got? Entropy change in reversible isothermal process, entropy change of the system is NR ln V2 by V1, because NCV ln T2 by T1 part is cancelled. It is isothermal, temperature constant. And entropy change of the surrounding is just negative of this one, minus NR ln V2 by V1. So total is 0. All these things I derived in my last video. Now reversible adiabatic process, for the system also entropy change 0. For the surrounding also entropy change 0. Total is 0. In the system, there I told you why entropy change is 0, because in case of reversible adiabatic process, entropy change due to change in temperature is exactly compensated by entropy change due to change in volume or pressure. Now reversible isochoric process, where volume is constant, entropy change of the system is NCV ln T2 by T1, entropy change of the surrounding just negative of it, so total is 0. Reversible isobaric process, entropy change of the system is NCP ln T2 by T1 and the surrounding is minus NCP ln T2 by T1, just negative of it, so total is 0. Irreversible isothermal process, entropy change if for free expansion, that will be NR ln V2 by V1 plus 0. Entropy change of the surrounding will be 0. But if the expansion takes place under constant external pressure, then entropy change of the system NR ln V2 by V1 and the surrounding minus P external delta V by T, which is greater than 0. Okay. An irreversible adiabatic process, entropy change of the system is same, that is NCV ln T2 by T1 plus NR ln V2 by V1, which we derived earlier. And entropy change of the surrounding is 0, because no heat is released by the surrounding. So total is greater than 0, that is positive. So entropy change in all irreversible processes are positive. Irreversible processes are spontaneous. So entropy change, that is total entropy change of the system and surrounding, is positive for spontaneous or irreversible process. And for reversible process, total entropy change is 0. Hope you have understood. Thank you.